Welcome to part 2. In this part, we are just going to prove this technical lemma, which is used to finish off the change of variable formula. And we got all the star values and hat values out of using mean value theorem. So let me summarize what we have here. There are two items, and the first item looks like a typical two-variable Riemann sum. There's a function g and a double sum, and another function with a different special value chosen for kjth cell, and multiplied by the area of that piece, delta xk and delta yj. Then it should approach this one. Proof of this one is fairly simple, and you put that one and actually divide this Riemann sum. Riemann sum behaves nicely with the sum of two functions, so you can separate these two into one Riemann sum with g with this area multiplied and another Riemann sum with h in it. Individually they approach some number, because we assume this g and h have this property, and therefore they have integral defined. So that part's fairly easy, and this one had to be treated slightly different because it's the product of the thing. So we're going to look at the proof of this part 2, and hopefully you can imitate the part 2 and do the same thing with the part 1, which I find is a lot easier to do than here in the part 1. So let's take a look at the proof of part 2 here. So here's the beginning. This is part 2 of the lemma we're about to prove, and we want to show this approach is as following. If you look at this integral and try to rewrite this one as a Riemann sum expression, that would look like the following. Here's a 2 double sum, and g and h multiply to each other with the same special value applied to these two functions as a product in here, and multiply that. So this is our target, and if we have this one, we can easily replace this one actually with this double integral version. What we actually have is this one, so I wrote down here. So this is not really a double integral. They're supposed to approach double integral, especially the first one I wrote here, supposed to approach this double integral. So I'm taking the measuring the difference of these two things. If I can show the difference of these two things approaching 0, then whatever this one goes, this should go follow. So that's the rough idea. So since this g of x star part is a common, so you can factor out, and what you're left with, and this delta xk and delta yj part is also common. What's different is this h part. So after you combine these sums together and factor out common factors, this is how it looks like. So there's hxkj star from our target, and what we actually have is h of x hat. So it's really about controlling this term. So let me explain. We're about to show this quantity, which is equal to this absolute value of difference right here, and we're about to show this is approaching 0. Therefore, this one we have is almost equal to that. So why is this approaching 0? The reason is the following, that we have g multiplied against to this delta xk and delta yj. So if we don't have this factor, and what we have here is a typical Riemann sum, it's not going to approach 0. But there's a multiplicative factor inside, and where h is evaluated almost the same point. So that turns out as another multiplicative factor, kind of uniform multiplicative factor. That's the hard part to establish. But there's a uniform multiplicative factor kicks in, so that the rest of the part is a finite part, g and delta x and delta y, because we assume g is a Riemann integrable or continuous. And there's additional factor that makes this whole thing goes to 0. So if it's a double Riemann sum, if there's a 2 multiplicative factor that approaches 0, delta xk and delta yj is small, and that's enough. If there's another multiplicative factor that approaches 0, so it's like order 3 is too much, then eventually it's going to go to 0. So that's a rough description of how why this one goes to 0, but mathematical proof is a bit more rigorous than that. So I'm going to simplify notation a little bit, and let me show you what's up there. We have this thing, and this is what we want to show that approach 0. There's this kj all the time in the following argument, so I'm going to abbreviate to just x star and x hat and so on. So what we're going to do is that we're going to look at that h, difference of that value, and we're going to measure. Let me show you it again. It's a bit confusing. I think I'm supposed to say something else. Or we're back here with this notation of x star and x hat. This will be x star and y star minus h x hat and y hat. So we're going to use mean value theorem and to the one variable at a time to break this one down into in terms of derivatives, right? Again, there's a mean value theorem. So we're not going to do this simultaneously. Why? And we do not have a theorem. So we have to look at, we don't have such a theorem, so we have to look at one variable at a time. So that's why we have the following. Okay, so I am looking at one variable at a time. This time I'm looking at the y value. So y is different. There's a y hat and there's a y star. So that's why I had this y hat and y star. But let's fix x to be x star here. So we can apply mean value theorem to the y variable. All right, so let's look at this function as a function of y, then input y hat and y star is different. So we have y hat minus y star in the denominator. Then it's going to be the special value of a derivative. Here y is varying, so it must be partial y. Then we have a special value y, so I'm going to choose this tilde symbol. Hope you can distinguish my tilde from hat. So this is a new symbol, tilde, so there's a special value. So I want you to go in and take a look at the original function and do what I just did to the other parts. Let me show you. So this is the thing. Then we realize these two y coordinates are different. So keep the x coordinates the same. And I chose x star and figure out how to rewrite this one slightly different. It's not exactly this, but it's going to connect us. So I want you to go and try. This time you're going to fix y coordinate over this one or that one. Try whatever you want to. And keep this difference of this x coordinate x star and x hat and apply mean value theorem. So you may pause the video and see what you have. All right, I hope you found its calculations are similar. I already told you that you had a choice that when you do this, apply the mean value theorem to x coordinates. You have to make a choice of whether I'm going to keep this y coordinate as a y star or y hat. But I kept it as y hat, but you can still do this with a y star. But I realized that if I have y hat, something nice happens when we combine these two things together. So, namely, that h of x star y hat I had it before appeared again if I do this y hat. So that's why I chose y hat. I don't know what's going to happen if you choose y star there, but y hat does something nice. So I chose y hat. So x star and x hat here, and apply the new mean value theorem, and there's going to be a special value on the x spot there, and derivative is going to be partial with respect to x. So I do have a few more things to say here in this part. What is it? It's the following. What we want is h of x star, y star written in a different way, and h of x hat and y hat written a different way. So that appeared here, and that appeared there. So we're going to solve these two equations for these two terms so that we can rewrite this one. All right, this might turn out a little bit small, but let me do this. So we have these two equations out of mean value theorem. If you solve for hx star and y star, and this is what you get. And hx hat and y hat is to get. This is another part that you might want to do, that it's not something difficult and you feel understand much better about what's going on. So pause the video and see you get my answer. So I'm just showing that what I get here in a little bit bigger picture. So when we isolated this star part and the hat part here, and this is what I get. Okay, so there is this common function value appeared, and plus some zero factors because they're very, very close to each other, right? They're in between xk minus 1 and xk, and yj minus 1 and yj, so they're going to be the contributing factor, the zero factor here. So, and this is not necessarily these coefficients are zero. Okay? So we can take the difference and something nice will happen, especially with this choice of y hat and x star there. So here it is. If you subtract those two equations, let me show the whole thing. So here it is. So we have hx star and hx hat, those things figured out here. And if you subtract the second row from the top row, you can see these two cancels. All right? So I wrote this one, simplified notation. This is not exactly delta y. Delta y was that yj minus 1, but they're intermediate special values of that interval. So I used a different notation. So I chose the star, so that's going to be delta y star. And just to be consistent with the way the star, the order of the star and hat appeared, I chose this one to be negative delta x star. But I don't think this negative really matters here. So I just copied down these two things. So that difference appeared in that sum is rewritten like this. So the uniform kind of zero factor is controlled like this with this delta y star and delta x star. So I'm showing this part again that we're about to rewrite this one again, and then we looked at these difference of star values and then hat values and rewritten in terms of partials. So here it is. There are lots of xkj stars and float around, but I just abbreviated like this to the important part. All right, so that's the one equation we showed it earlier. That equation goes there. Now, one thing I didn't explain is this: how this absolute value goes inside the sum. So I hope you understand what a triangle inequality is, and that the absolute value was applied to the entire sum, but that absolute value now appeared every term here. So that's not equal. Then because you turn every term into an absolute value term, all the term turns to a positive, so eliminating all possibility of some negative cancellation. So that makes the entire sum necessarily bigger. But this is still small enough to conclude this one approaches zero. So what goes from here to there, turning all the terms into positive, everything multiplicatively and additively, everything has this absolute value around. This is called triangle inequality, and that's obviously a bigger quantity. So absolute value of g is there, and we have this positive zero factor appearing. This hy, the partial values, and hx partial value, they're not necessarily approaching zero, but they're not going crazy. It's absolutely bounded, and that's the crucial part of this argument. Let's look at the next line. So what I'm doing here in the next line is that, let's look at everything, and everything is a positive, and this delta y star is some intermediate difference in between that interval yj minus 1 and yj. In particular, this cannot be greater than delta yj. It's a shorter interval length. The same here. This delta x star was, let me show you here, x hat minus x star, so that they're all intermediate value in between xk minus 1, xk, so difference cannot be greater than the delta xk. So hence this inequality, each of these interval cannot be greater than this interval that we started with as a part of the Riemann sum definition. So we have this inequality. Let's look at the next one. Okay, in the next part, I'm just distributing here. So I'm multiplying this one to that part and write it out. So we have this term, multiplying this term to multiply it here. So there's a second power of delta xk star. So write it out. And then we're going to do, see this, the next part is important. Let me show. Okay, I'll just slide it up. So what we have here is that because the reason these guys are going to zero is because there is this additional degree 3. Here's one part going to zero and two 2 copies of a 0 factor, and same here. And what is happening to the value of g and hy and g and hx, it's bounded. We're looking at this entire thing over a closed little region, so the continuity of these functions that gives a bound. This is absolutely bounded by some absolute number. So altogether, this g and hy, or g times hx, everything is bounded by a single number which is determined by these function and the region R. So if I replace this thing with this m, I'm making the quantity bigger. Before was the exact calculation right there. So we have this, and m is now, it's not changing with respect to k and j, so they can be factored out. So that's this part. M is factored out. Then I separate this Riemann sum into 2 pieces like this. So again, this delta yj squared is rewritten like this, delta yj and delta xk and delta yj. So let's think about what this delta y bar is. So I should have written one more line for you to easily understand what this is. If this is exactly equal, then there is going to be delta yj there, and there's going to be delta xk. But I replaced those additional copy of this one with this maximum possible value. So let me show you here. So here it is. For each of the partition of x side and then y side, we're going to have this different partition, and these are not necessarily regular or uniform partition. So we have lots of values. The interval, first length, and there's m interval, so there's a length of mth interval. And here is the first interval for x side and the length of nth interval in the next side. So what this delta y bar and delta x bar is notating is maximum value of these intervals. Okay, so all we have to show is this is approaching 0. So to simplify this complicated sum, we keep replacing the part that is important part with this maximum value, so that we keep this direction of the inequality. So again, replacing these, some of the factor to the maximum part is that this is no longer varying with respect to k and j, so treated as a constant can be factored out. So again, when we replace one of the factors here and there with this maximum value, and we make this one necessarily bigger. So we have this inequality, and this one will be factored out. So this is what we have over there. Again, this delta y bar factored out and delta x bar factored out. And nice thing about this part here, if you think about each of this product is the area of the one of the piece of the region R, and that's the same here. So if you add all this up, it's going to be just the area of the region R, which is why it looks like this. That is going to be A, exactly A. So there's no inequality this time. It's exactly A, and that's exactly A. So altogether, it looks like this. A is the area of the region R over which we're considering this entire integral. M is the maximum value of some function involved in here over this region R. And then it looks like this. Now, this is a lot bigger than the one that we started with, but it's good enough because in between there is this quantity we want to compute, and A and M is not changing as we divide the region R into finer and smaller pieces. This A and M is not changing. A is the area, M is the maximum value of the function over the entire region. So only thing that is changing, it is the maximum length of the interval, because we keeps chopping it down to a smaller interval. The maximum length of the interval we're having is also approaching 0. So by squeeze theorem, whatever that was in between must approach 0 as well. Okay, so we proved the lemma, and let me show you again that this was a repeat of part 1, the original part, just to help you to remember what that was about. So we had the following Riemann sum, and out of the mean value theorem we have 2 different kinds of special value kicked in. namely the star values and hat values. And as we multiply, and this is the area part, area of delta A, this part here, multiplied by the original function value. And in that, when we do that, we have this a mixture of star values and hat values. So because of that lemma, we can just disregard these different types of a special value and treat it as one special value and turn everything into the Riemann, the double integral, which is shown in the below. So that sum with that old stars and hat value turned into just x and y, and it nicely turns this entire thing to this double integral form. So that was the use of that lemma that allows us to, with this cancellation, that allows to conclude the double integral is rewritten in terms of this new parameter with this Jacobian factor kicks in. So that's to prove that this Jacobian factor is a sufficiently captures the value of the double integral. Thanks.